I could have been demonstrating the conservation of momentum with a collision of billiard balls, or the law of reflection as a ball bounces off the band. But in fact, with that shot, I was trying to make a completely different point. Unless you've seen me on television before, it would be hard to tell that that shot was taken through a mirror, because the motion of billiard balls on the table is as natural when viewed through the mirror as it is when looked at directly. But is there no way in which you could tell a mirror image from the real thing? Well, let me just continue here.
So we had to wait until we left the snooker table before we could tell which was the proper right or left of that scene. Paul Clark's right side looked very much like his left, and so indeed did the sides of the table. But most things aren't that symmetrical. If you look around your lounge, for instance, you will see many things that look different in a mirror. Take your television set, for example. The knobs are probably all on one side. Or a plant. That's hardly symmetrical. But the question which interests us here is not just whether we can tell left from right using certain objects, but whether we can find an unambiguous way of distinguishing left from right using the laws of physics, which are supposed to apply to all objects and all situations. In an everyday sense, telling left from right may seem pretty straightforward. My heart is here, so this is my left. In the snooker scene, Paul Clark's heart would be on his right side. So if we were able to look beneath the surface, you would know that what you are seeing here is the mirror image of a person. But when you see me, with my heart beating here, you know it's a real person. But unfortunately, things aren't that simple. As physicists, we have to look for rules which can't break down under any circumstances. The question we must ask is, if a human animal arrived from outer space with a heart which appeared on his right, would we have to assume we were looking in a mirror? In this program, we're going to show you how hard it is to distinguish in a fundamental way between left and right, between reality and a mirror image. The key question at the outset, though, is what we mean by fundamental. You may think that you don't need a fundamental way of distinguishing between a mirror image and reality, because there are so many everyday ways of doing it. But you have to be careful. This looks a common enough scene. The cars and road are familiar, but look closely at the surroundings. The vegetation looks vaguely subtropical. The cars look American, and yet they are driving on the left. Could this be the scene of a former British colony? Or is there something quite wrong? To decide that the scene is not genuine, we need writing to reveal that the shot is a trick shot, presented the wrong way round. But writing is a convention which we are taught. If we saw this road sign, for example, most of us would have a job to tell left from right. So such distinctions are cultural rather than physical, and could easily be reproduced in mirror fashion. They tell us nothing about the fundamental laws of physics. Well, one reason why you couldn't tell if the film was the right way round until we got to the writing was that design systems like cars and motorways often have variants which are also in common use. In England, we drive on the left, in America, on the right. But not all designs have mirror images, which are themselves common. Around the house, you'll find many objects which are usually designed only one way round. Take this telephone, for example. I can have the receiver on the left or on the right. But if I want to make a call, then I must dial clockwise. Let's have a look at that in a mirror. In the mirror, I appear to dial anti-clockwise. And I've never seen a telephone designed like that. Here's another familiar object, and of course it works, like this. But because I'm left-handed, I can use something rather different. I can use this left-handed corkscrew, which works like this. Now, let's look at that in a mirror. What you see in the mirror looks like a normal right-handed person using a normal right-handed corkscrew. So this was a situation in which the mirror image was really quite familiar and the reality was rather unusual. Now, the purpose of looking at these objects was not just to get the wine, good though it is. What I wanted to demonstrate was that we need to do two things to refine our question of distinguishing left from right. You see, whatever we mean by left and right, it gets changed round in a mirror. So if there were a fundamental distinction between left and right, there would be a distinction between the mirror world and reality. There would be some mirror images which just never occur in the real world, which are physically impossible. So what we must do is to see if we can reproduce mirror images in the real world. And that the first thing that the corkscrew gave us was a clear sense of left and right, using a circular or spiral sense whose mirror image is a different spiral. And the second point is that we have to study the forces that are operating in the situation. And with the corkscrew, the characteristic of the force was that most people turn corkscrews like this. Now, if we turn away from manufactured objects to the natural world, we find situations which are far less easy for us to manipulate. And the obvious place to study natural processes is on the surface of the Earth. And if we get above the surface of the Earth and look at satellite pictures, then we see very interesting weather patterns. And this one here is called a cyclone. This is a cyclone in the northern hemisphere, and in the centre there's a region of low pressure. The air, as it spirals in towards the centre, moves anti-clockwise. Now let's look at that in a mirror. In the mirror you see something different. The air, as it spirals in, appears to move clockwise. Now, does something like that happen in nature? Is it reproduced elsewhere? Well, in fact it is. Here, on the reverse of the book, there's a picture of a cyclone in the southern hemisphere. And I think that you can see the air, as it spirals in, is moving clockwise. And indeed, the law of conservation of angular momentum ensures that the mirror image of a cyclone in one hemisphere is reproduced by a cyclone in the other hemisphere. So cyclones don't help us to distinguish left from right. They have mirror images which are found in nature. But cyclones are produced by a very complicated pattern of forces involving gravity, rotation, and differences in pressure. What we want to do is to study the fundamental forces of physics, one at a time. In other words, we need to look at processes in which only one basic force is dominant and see if that distinguishes left from right. If it does not, then more complicated processes involving this force become problems of detailed design rather than basic physics. By studying fundamental forces, we should then be able to find out if our mirror man is possible, and much more besides. So let's start off by considering the force with which we're most familiar, the one which keeps me sitting on this settee, the force of gravity. In our solar system, we know the planets move round the Sun in accordance with Kepler's laws of planetary motion, which follow from Newton's laws of motion and gravitational attraction. The planets are moving round the Sun in ellipses, approximately in circles. They sweep out equal areas in equal times, with periods related to their distances by Kepler's third law. Now let's go through the looking glass. What you see is certainly different. But are Kepler's laws still being obeyed? Well, the planets still move in ellipses. They still sweep out equal areas in equal times, and they still have periods and distances related by Kepler's third law. So, can such a mirror solar system exist in the real universe? Well, we can reverse the model, but we clearly can't build a full-scale version of the solar system itself to test this with all the planets going the other way round. But we think we know enough about the laws of motion under gravity to say that the mirror image of our solar system is physically possible because it obeys the same rules, and it could perhaps be found in reality elsewhere in the universe. Well, perhaps this is no surprise, because gravity is a simple force which points from one mass to another, from this golf ball to the center of the Earth, for example. But the other force with which we are very familiar is rather different from gravity. A device like this fan is driven by currents and magnetic fields. And some of you may know the left-hand rule, which tells you how such forces act. A rather complicated force law is involved, and what we want to investigate now is whether we can always find situations in the real world in which we can match electromagnetism as seen through a mirror.
Here's a very simple situation in which we can see electromagnetic forces at work. We just have two wires that can carry current. So I'll switch the current on. When the currents are running in opposing directions, the two wires repel each other. Now, when I switch the current so that they're running in the same direction, the two wires attract each other. Now, what does this situation look like when viewed in a mirror? So let me switch the current on. Now the image that you see in the mirror is precisely the same as the image you looked at directly. The two wires attract each other, and the two currents are running in the same direction. But if I switch the current so that they're running in opposing directions, in the mirror image, the wires are repelling, and the current on the left is going up. Now what we want to do is create a situation in the real world that exactly matches the mirror image you were looking at. That is, we want to see the wires repelling and the current on the left going up. But what do we see in the real world? We see the wires repelling, but the current on the left going down. What I have to do is to switch both currents at the same time. I now get repulsion as before, but this time my up arrow is on the left and my down arrow is on the right. So using a simple circuit like this, you can see that it's easy to reproduce in real life any image that you look at in the mirror. So let's look at something a little more interesting. Here we only have one current carrying wire, but we placed a small magnet near it. Now what will happen to the magnet when I switch on the current? With the current running down the wire, the magnet orients itself so that the black end is running counterclockwise around the wire. If I switch the current the other way, then the magnet reverses itself. With the current flowing up the wire, the black end orients itself to be clockwise around the wire. Now, what's going to happen to all this when we look at it in a mirror? In the mirror, you find that with the current flowing up the wire, the black end of the magnet orients itself in the anti-clockwise direction around the wire. If I switch the current, then the magnet reorients itself. Now, can I produce a situation in real life that is exactly the same as this mirror image that you're looking at? Let's have a look. Here we have a very similar apparatus, one wire, a magnet. Let me put on the current. Now let's compare this situation with the mirror image, which we mark as M on your screen. We find that the two images are not the same. The magnets are oriented in opposite directions. So I've got to change something. Well, I could change the current. Now that's fixed up the magnets all right, but still the images aren't the same because the currents are now flowing in opposite directions. So I haven't matched the mirror image situation. So let me put the current back. Now, changing currents hasn't worked, so I really do have to change something else. Well,
I could change the magnet. Now when we compare mirror images, we find the two images are exactly the same. The currents are flowing in the same direction, and the magnets are pointing in the same direction. So I am able to reproduce in the real world exactly what you see in the mirror image if I use a different magnet. But you may say, all right, all he's done is paint one end of the magnet white and the other end black. And that's a bit of a cheat. But if all I'm trying to do is reproduce here exactly what you're looking at in the mirror, then I haven't cheated at all. But we may have used a very simple experiment. By way of analogy, let's think back to the beginning of the program in which you found it difficult to tell the mirror image of me from looking at me directly. But if you'd had a stethoscope, you could have told very quickly the real me from the mirror image. All right? Can we use a more complicated system of currents and wires and magnets to set up a situation whose mirror image you can't reproduce over here, and therefore you would know that painting the magnets end for end was a cheat? Well, we could use this piece of wire, a coil, which I can run a current through by plugging it in here. I bring it in close to the magnet, and I find that with the current running in this direction, it attracts one end of the magnet. Doesn't matter which end is painted, it'll pick out one end of the magnet. So can I use an apparatus like this, set up an experiment whose mirror image I cannot reproduce? Let's go have a try. All right, I switch off the current, and I get the coil. Now, what does that look like when viewed through the mirror? The white end of the magnet is attracted to the coil, and the current is flowing from the magnet end of the coil to the other end. Now, can we reproduce, using apparatus 2, exactly what you're seeing in the mirror? In fact, we already have. When we compare the two images, we find that they're exactly the same. The white ends of both magnets are attracted to the coil, while the current in the coils are flowing from the magnet's end of the coils to the other end of the coil in both cases. Now, if we disconnect the currents in the coil and turn on the current in the central wire, we also find that the mirror image situation and the real situation of apparatus 2 are exactly the same. So we've been able to reproduce all the phenomena in the real world that you have observed in the mirror.
We believe that no matter what combination of magnets or wires we use, we can always reproduce the mirror image. Now, the laws of electromagnetism that govern all these phenomena also predict the existence of electromagnetic radiation, light, radio waves. And furthermore, the laws of electromagnetism, combined with those of quantum mechanics, allow us to understand the structure of atoms and molecules. So, if we do an experiment in which light interacts with matter, we should still be able to reproduce the mirror image. With this apparatus, I can study the interaction of polarized light with matter. I have here two pieces of Polaroid. The first one only lets light through that wiggles like that. And I can extinguish all such light by turning the second Polaroid like that. But what happens if we put a sugar solution between these two Polaroids? The light that goes through the sugar now gets through the second Polaroid. In order to achieve extinction, I must rotate the second Polaroid to the right. Now, what does this look like when viewed in a mirror? It looks as if the Polaroid has been rotated to the left. So now I have to reproduce in the real world the mirror image that you are looking at. And just as in the case of the magnets, I have to change something. I need a new sugar solution. Now to achieve extinction, I must rotate the Polaroid to the left. And this exactly matches the mirror image that you were looking at. Now these two solutions are made up of different sugars. They do different things to light, but is there any other difference between them? Well, since one rotates light to the right and the other to the left, it should hardly come as a surprise that their molecular structures are mirror images one of the other. This difference in structure explains their different effects on light.
But there's another difference between these two sugars. This tea doesn't taste at all sweet. But if I try the other sugar, then it does taste nice and sweet. The reason is that this difference between left and right-handed molecules carries through to our own chemical structures as human beings. So we find one of these sugars, this one, sweet and pleasant, whilst the other isn't at all. So the biological world is rather complicated. Indeed, plants, as well as human beings, have left or right-handed preferences. Plants are fascinating examples of natural design, and there are two here which we want to look at more closely. You may recognize this honeysuckle, which is always found to grow in a spiral called a left-handed helix. On the other hand, there are plants like this bindweed, which always grow in the opposite sense, in a right-handed helix resembling a normal right-handed corkscrew. But the really interesting thing is that the type of molecule responsible for genetic coding both in animals and plants has itself got a helical structure. The structure of DNA was found in 1953 to be a double helix spiraling up like a right-handed corkscrew. So the molecules responsible for the coding of the characteristics of living organisms are themselves helices. And what does this tell us about the architecture of living things? Well, although right-handed DNA makes up our own coding, we know of nothing in the forces between atoms which says that exact mirror image molecules can't exist. In the case of sugars, we could actually make them. For more complex molecules, we can't yet do that. But a form of life based on the mirror image of our own molecules is entirely possible, because the electromagnetic forces which govern atoms and molecules can be reproduced in a mirror form. So we would not have to rewrite physics if someone produced a right-handed honeysuckle or even a left-handed bindweed governed by the opposite DNA, nor if a mirror Paul clock arrived from outer space. Now, gravitational and electromagnetic forces are not the only fundamental forces which are known to physicists. Inside the atom, new forces have been found which govern the way nuclear particles behave.
There are two forces at work in the nucleus. The strong force holds the nucleus together, and the weak force controls the decay of individual nucleons. Now we can study the strong force in collision experiments. And no distinction between left and right has been found in such experiments. But in 1956, decay processes involving the weak force revealed for the first time a fundamental distinction between left and right, between a mirror image and the real world. But that's another chapter in our story.